Good morning, students. In the previous class, we stopped in the part of the derivation or some points related to the mobility. Definition, units are very important for 1 mark question only. This point is important for 1 mark question. Mobility, as an indication, mobile means moving. Mobility means movable, easily movable or not. So, for the electrons or charges moving inside the materials, how that mobility is there? Mobility is more means freely moving. Freely moving means we can take easily current. Not able to move freely means difficult to move the current. So, mobility is related to what? Mobility is electrons are moving because they are in the particular direction electron movement, not random movement. In the particular direction they have to move. The particular direction, some kind of motion in particular direction, that is we call as drift velocity is there, and that is produced because of the electric field only. So, the mobility is defined as the ratio of magnitude place. Why? Because drift velocity is negative. Expression we get in terms of the electron charge, negative charge. So, drift velocity is magnitude only here for the definition purpose also please mentioned as a magnitude. It is a ratio of magnitude of drift velocity and electric field. Electric field applied for the conductor etc. is not required. That is you have to understand. So, if you take a conductor and if you apply the potential difference reciprocity, you get the electric field produced inside, produces the electrons travel in some acceleration and you get the drift velocity due to the collision of the electrons with the atoms. More collision means automatically the velocity is less, but for the given materials, these things are constants, approximate ranges. So, mobility mu. So, mu is a simple name for mobility equal to Vd by E. Vd is a drift velocity, magnitude we are taking. This is a modulus, means magnitude means don't take negatives and you take only the positive. Vd, where Vd is a drift velocity, E is the electric field. So, Vd is equals to, already we know this relationship, Vd equal to minus E by M into tau. E is the charge of the electron, M is the mass of the electron, E is the electric field applied inside the conductor, and tau is the relaxation time. Relaxation time is the time under which there are two collisions, successive collisions. Charge of the electron, mass of the electron, relaxation time. Time interval between successive collisions of electron with the atoms. And if you substitute this mu, Vd, for mu, if you substitute for Vd, E cancels. So, electron term will be mu equal to E by M into tau equal to 1 by E. That E, Vd by U, you know, E cancels, relativity cancels. The resultant is mu equal to E by M into tau into E by M. Charge by mass, that is for the specific charge of electron. Specific charge of electron is constant. Specific wording we are using it means per unit mass. Specific charge of electron is E by M is constant. So, finally, mu depends on what factors means only tau. Even though you are taking the relation terms to Vd and E for definition purpose, this mobility do not depend on the electric field or other factors. It only depends on the relaxation time tau. Relaxation time depends on what factors is, depends on the nature of the material, means how the atoms are arranged. If the atoms are very close to each other, electrons has to collide with many atoms, automatically relaxation time is less. Atoms are close means tau is less. If the temperature increased, then in that case collision probability increases, quickly collides. Quickly collide means what? The time interval decreases, tau decreases, mobility decreases. So, increasing temperature mobility decreases. Decreasing temperature mobility increases. You can say that relationship. So, here finally mobility depends only on the nature of the material and temperature that you have noted. That is for concrete atoms. Mobility is, but one question they will ask for the PU theory also is that does it depend on the electric field? Answer is no. Formula is there, but actually do not depend on the electric field because electric field is also present in the expression of drift velocity. Next is mobility is a scalar quantity and is always positive. When I take the modulus, so then it is always positive. Mobility is if mobility is more, what it actually indicates meaning is if mobility is more, then indicates that the electron can move freely, more freely. More mobility, more freely. Less mobility indicates difficult to move. Next is SI unit of mobility. SI unit of mobility, from the definition we can take the relationship mu equal to V by E, velocity by electric field. Velocity is units, SI unit is meter per second. SI unit is meter per second. And electric field we have 2 units for this. Newton per coulomb, one formula, basic definition equal to F by Q naught or F by Q, force by charge. Another unit is electric field is equals to V by R or minus dV by dr relationship is there. So, based on that also you get the relationship volt per meter. Electric field has 2 units, positive units, Newton per coulomb, volt per meter, both are acceptable for the SI units itself. Then putting these in units here, you will get the relation as this is going to be meter per second, electric field is volt per meter. So, this is the units we need to know. This where relation given is in terms of the textbook relation they mentioned is this unit only. Okay. So, textbook units, textbook points you need to take it. Next, other possibilities in terms of Newton per coulomb also possible. This can be asked for the complex units. Okay, in terms of Newton per coulomb, E comes to the denominator, no? So if it is coulomb go to the numerator, per Newton you will get meter per second is for the last relationship. And in your textbook even they will give us centimeters also. You know how to convert it to meters and centimeters. That's not important for us. This is only important. Next is relation between conductivity. This will be asked for the competitive exams only. Okay, and this relationship will be getting again in the semiconductor topic for the competitive exams purpose only, not for PhD. So relationship between the conductivity sigma and mobility. Microscopic formula for the sigma is n sigma is equal to n square tau by m. N is this n, small n. Small n indicates is free electron density. Number of electrons per unit volume. Free electrons. Electrons will be there for every atom compulsorily, but we are able to move freely one atom to other atom. Those electrons only we need to consider. That is only for conductors we consider. Insulators, there are no free electrons available unless the temperature increases. But we are not talking about high temperature, we are talking about normal temperature conditions. So normal energy is a room temperature. Sigma equal to n square m tau by m, whereas mobility mu is nothing but equal to e by m into tau, where n is free electron density. What is unit for this free electron density? Is units electrons, number of electrons per unit volume. So per units are taken as per cubic meter. In per cubic meter, number of electrons per unit volume. This will be mentioned in terms of per cubic meter. Next is take the ratio of these two. You will get the relation sigma equal to mu n t. Is a relation between the mobility and sigma, means conductivity in terms of small n. More n, already we know that more sigma. Next, mobility is independent of electric fields. This point is also important for competitive exams, also be there. Mobility depends on what factors there? Mobility depends on only nature of material and temperature. How does it depend on temperature? I will discuss in the next point. Continuation of the previous point. Mobility is directly proportional to relaxation time. That means if the temperature increases, if the temperature increases, tau decreases, mobility decreases, and vice versa. If temperature of conductor is increased, then relaxation time tau decrease, therefore mobility decrease, therefore mobility mu of electrons decrease. We are going to discuss later semiconductors like silicon, germanium. We are going to discuss later that relationship. You will get the positive ions, negative charges will be there. Semiconductor case is different. There increase of temperature, mobility increases. For the conductors only, this is only for conductors applicable. Okay, not applicable for semiconductors. That we are going to discuss later. Next is dimensional formula of mobility. Velocity by electric field, and velocity dimensional formula is velocity equal to Lt minus 1. M if you want, M0. And electric field is force by charge. Even if you take up the V by R also, the dimension formula will be the same. Dimension formula won't change. For one physical quantity, you can have the different units, different formulas. One physical quantity always will have only one dimension formula. Dimension formulas basically do not change. Units you can write many number of times. Okay, and formulas also can be many types of that, but not dimensional. Dimension only one. Equal to F by Q. What is the force dimension formula we have is F equal to mass into acceleration, m/t minus by charge. Charge in terms of current weight, I equal to q by t, q equal to I into t or a into t. So here is this term becomes m minus 1 lt minus 3 I minus 1 is electric field. So we'll get the relation for the mobility. Mu is equals to dynamic moment of velocity lt minus 1 by electric field m minus 1 lt minus 3 I minus 1. We get a error cancels. L cancels. M minus 1 becomes equal to m. T minus 3 take it to the limit to equals to plus 3. Plus 3 minus 1 is plus 2. T m0 t square I only I to the power of 1. And I can represent a. So that formula is your m L0 or simply t square I can take. Is the relation of mobility. In place of I, there is some books they mention A, some books they mention I. Better take it as A, according to your textbook relation, but complex is not fixed. Dimension number for current can be taken as I also, A also. Possible. These are the points related to mobility. Is limitation of Ohm's law. This is asked generally for 2 marks question or rarely asked for 3 marks question and we asked for one limitation. Ohm's law is applicable only for the conductors which obey Ohm's law called as ohmic conductors. What is Ohm's law? Ohm's law states that V is proportional to I. Conditions: temperature constant and the physical dimension of the conductor should be constant. That is what we give the definition here. But in which case it is not applicable. Means V is not proportional to I, automatically Ohm's law is not applicable. Okay, correct textbook relationship they have given. If in case V is proportional to I, then what happens is, first I am not writing the limitations. Definition of Ohm's law I am revising this. In the examination, don't mention of Ohm's law is V is proportional to I. Ohm's law is at constant temperature for given conductor. For given conductor means area length should be constant. Okay, this is the Ohm's law. So V is proportional to time means if you take the graph, how do you reach? Relative proportionality means you will get the straight line. V and I graph must be straight line possible to all. Okay, if V and I graph is not straight line means automatically it is not going to obey Ohm's law. So those conditions we will discuss. One thing is V proportional to I, just listen on the V proportional to I condition satisfied. Means graph VI graph should be straight line possible to all. What happens if you reverse this voltage? Negative means V is reversal. Voltage of battery is reversal. Current also gets a reversal. So if V is reversal, current also gets reversal. But value will not change. For 10 volts, if I am getting 2 amperes, if I take minus 10 volts, you get the again 2 amperes only. For 10 volts, if I get the 2 amperes current. Minus 10 volts, if I take this reverse of this battery, if I have done minus 10 volts, you will get and you will get the current equal to again 2 amperes only. Same current but in opposite directions. So this graph is straight line passing through the origin, and if reversing the voltage, current magnitude is not reversible, but only direction is reversible. For the same conditions, if we are taking the forward and reverse conditions, then Ohm's law is applicable. Okay. And for the given voltage, you should have only one current, not multiple current. Okay. That conditions are applicable. Only then we can apply the Ohm's law. For some materials, it's not applicable. Like semiconductors, I told you, Ohm's law is not applicable. Only for conductors is applicable. Which materials for which you can apply Ohm's law are called as ohmic conductors. Which do not obey Ohm's law are called as non-ohmic. Then they may ask you the examples of the ohmic and non-ohmic also. Points. Ohm's law is applicable only if potential difference, only if V is proportional to I, where V is potential difference by current, and Ohm's law is not applicable is not applicable if potential difference V, if potential difference V, capital V, is not proportional to current. That means what? VA graph, this must be a straight line. If VA graph is not a straight line through origin, Ohm's law is not applicable in this sense. Under the same point I am writing. Not straight line. Written like for not applicable. Graph is, if VA graph is not a straight line, then Ohm's law is not applicable. Next is reverse voltage. If potential difference is reverse with the same magnitude, if potential difference is reverse with same magnitude, then current is reverse with same magnitude. Same magnitude. If potential is reversed with same magnitude, then current current is reversed with the same magnitude, then we can apply the Ohm's law. But current is not reversed, not in the same magnitude, Ohm's law is not applicable. Once again I revise this. We are discussing for the not applicable. If potential difference is reversed with the same magnitude, then current is reversed with the same magnitude. What we happens is, then Ohm's law is applicable. But we discussing not applicable means what it is? If potential difference is reversed with the same magnitude, but current is reversed with a different magnitude. I will change this to negative one. But current is reversed with a different magnitude. Then Ohm's law is not applicable. Next is, in case corresponding graphs are there, I will discuss the graphs. In case you take a particular voltage, for particular voltage, 1 current V is proportional to I. So for 1 ampere, 1 volt. So different voltage, different current. But in case same voltage, if you have the different currents, then in that case also it is not a Ohm's law is not applicable. For same voltage, different currents. In reverse also same voltage, different current, or same current, different voltage is followed. Reverse also possible. Current is possible for different voltages or vice versa. Find out. Then Ohm's law is not applicable. Example is last one. Example gallium arsenide. Gallium arsenide. GaAs. Gallium arsenide. For that we get the different. Same current is possible for the different voltages. Okay, gallium arsenide. So first case you take the V is proportional to I conditions. Graphs for downward condition V I. If they ask points, no, only these points will be mentioned. Graphs. Ohmic conductors, ohmic substances. This is extra conductor. Ohmic substances. When you can't ohmic substances, they obey Ohm's law. They obey Ohm's law. They obey Ohm's law, but ohmic substances. Example, all conductors like silver, copper, aluminium, iron, etc. Non-ohmic substances. And And for the case of ohmic substances, V is proportional to I plus. For this ohmic substance, compulsory V is proportional to I. Next is non-ohmic substances. They do not obey Ohm's law. What we discussed these points is for the case where they do not obey Ohm's law, they are already non-ohmic substances. Example for these non-ohmic substances is semiconductors, insulators, and semiconductor devices also, or vacuum tubes, diodes, transistors, and then thermistors, and even the gallium arsenide also. Compounds. These are the examples, some examples, etc. Okay. And about these semiconductors, diodes, diodes, two electrodes, we are going to discuss later. And the graphs related to this points. For conductors, if you are taken, we have graphs. This is also a part of it only, but extra points means they may ask you the graphs. But if they ask just for the literature also, that only you can mention. Conductors, if you take V is proportional to I. That means V graph is straight and passing forwards. This is V and this is I. The case of conductors. Generally, at high temperatures, the graph will deviate slightly. In the textbook, they mentioned as V here, I here. But generally, we take V on the x-axis, current I on the y-axis. But in textbook only for this graph they mentioned in reverse, doesn't matter. This is at high temperature or large current setting or high voltage setting. High voltage. At high voltages you will find small deviation there. But otherwise you must get the graph. This is for conductors. You will take V here, I here. Reverse it. You should do a straight line, same straight line. This is minus V, this is minus. Okay, this is a theta, this is also theta. What is tan theta? This is for conductor side. What is tan theta? Tan theta is equals to opposite side by adjacent side. This means I by V. V equal to IR, VR. V is equals to IR. So we follow the formula V equal to IR. What is I by V becomes is 1 by R. This is 1 by resistance. 1 by resistance is nothing but G, that is conductance. So what is this tan theta indicates is the slope of the curve. Slope we take is y-axis quantity by x-axis quantities. Slope of the VI graph. Carefully they will give you the problems for completing that. Suppose this one. The slope of VI graph when V is on the x-axis is equal to conductance G. Next is for semiconductors. This is for non-ohmic. Conductor diodes. Semiconductor diodes, this is non-ohmic. Means do not obey Ohm's law. For this graph, forward is different, reverse is different. This is a plus V voltage. Graph will be different like this. This is minus V voltage. I will be in milliamperes, but here I is in microamperes. In the previous case, this is in milliamperes, so this is also in same order in milliamperes. Only direction is changing. But here if for the semiconductor diode means two electrodes, two endpoints, two different materials, is called diodes. Having the two different materials, this type is one side, this is different. Conductor not like that. Conductor means wire. When you take a reverse the conductor for same direction, it makes no difference. But for semiconductor, it's not like that. So if you get the plus minus here, if you reverse it, current is different. The graph will be different. This is microamperes. This is a thing called the forward bias. Means plus voltages. This is a reverse bias. Bias means partiality. Every battery shows the partiality by showing the different voltage. Means higher voltage and low, plus and minus. Reverse bias.